Okay, so now we're moving on to a new kind of classification. So we've done double replacement, which is where a solid is made. We've done acid-base, where liquid is made, water in particular. We're going to do the gas ones in a minute. Right now we're going to do something called single replacement reactions, and they involve the transfer of electrons. In a single replacement reaction, an element plus a compound will produce a new element plus a new compound. That's how we classified it. And the way it works is if element is able to replace the like ion, and we'll talk about that in a minute, if and only if the element, this one, is more active than the ion that's in here. So if you want to think of an analogy, it's like a guy and a girl are dancing on the dance floor, and another guy wants to dance with a girl. Well, if he wants to come in and, replace the guy who's there, he has to be more, attractive, active, whatever. Okay, there's a little video online about this. It's kind of cute. Anyhow, there is this thing called an activity series, and for Mr. Lindenberger and Miss Packard's class, it's on the back of your periodic table. Miss Ellis, I know it's in your review packet. An activity series is a listing of how active elements are compared to the other elements, and it's literally a listing. If the element is more active than the like ion in the compound, then the element will replace it. And if the element's not more active, it will not replace it, and you will get no reaction. So if you notice, here are metals over here, and these are the nonmetals. It's only those four. And so the most active metal is potassium. That means if potassium is in a reaction with any of these other guys in a compound, so let's say SnCl2, Sn has no hope. Sn gets kicked out, and the K takes its place. Okay, that's what a single replacement reaction is. If you notice down here, those three at the bottom, these guys are the least reactive. Okay, copper's down here too. Okay, they are the least reactive. This is why they're considered coinage metals. That's why people make money out of them, because they don't tend to react with anything. They're not strong enough. So I can have a ring made out of gold, and it won't react with oxygen in the air. It won't react when I put it in water. It won't react when I put it in salt water. It won't react when I use shampoo. It just doesn't, because it's not reactive enough. That's why it's valuable. That's why we can dig it out of the ground. It doesn't react with, it can sit in dirt for centuries and thousands of years and react with nothing. Unlike aluminum, which you cannot dig out of the ground. It always reacts with something. It reacts with oxygen, reacts with sulfur, reacts with something. And then you have to purify it. You have to create the element. That's why, about the time of Napoleon, I think it was Napoleon, he had an entire silverware set, not made out of silver, but actually made out of aluminum, because at the time, aluminum was actually more valuable. It's harder to come by than silver. Nowadays, we use it to wrap baking potatoes, and then we throw it away. Hopefully we recycle it. But it's much more reactive than these guys. These guys don't do anything, okay? That's what the activity series is. So in a single replacement reaction, the element will replace the ion of like charge. In other words, they have to be in the same column. Positive replaces positive and negative replaces negative. It forms a new element and a new compound if it is active enough. If it's high enough on the chart. Okay, so you're going to use the charges to determine the formula of the product compound, and then the element is by itself. And watch out for the 7 diatomic elements. There are 7 of them. So, for example, Al plus FeO. So I'm going to go back and I'm going to look at that chart, and of course I don't have it in front of me. And what I'm looking for is I'm looking to see if my element is higher up on the chart than one of these two guys. Well, if I'm noticing in the chart, oxygen's not even listed in the chart. Aluminum is indeed higher than Fe. That means Fe gets kicked out. So you're going to have Fe all by its lonesome. And then the aluminum and the oxygen are going to hook up. And you're going to drop and swap charges on these guys. So you're going to get Fe plus Al2O3. So balance the equation. Put a 3, and a 2. Okay. Now this one. Now notice it's not written in the same order. It's not written element plus compound, but that doesn't matter. This is my element, and I want to see if it's going to kick out something that's in the chart with it. Well, I see magnesium in the chart, and I don't see any of these guys except hydrogen. And magnesium is indeed higher than hydrogen, so it's kicking hydrogen out by its lonesome. Now, when hydrogen exists as an element, it is one of my diatomic elements. It's always written as H2 when it's an element. When it's in a compound, you drop and swap. But when it's an element, you keep the 2 on it. Then I'm going to drop and swap with magnesium and nitrate, because they have hooked up, and what I get is I get HNO3 plus Mg goes to H2, and MgNO3 to balance it like that. Okay, let me erase this one. Okay, now this one, I'm looking at chlorine. That's my element. Okay, and I'm looking in here to see what else is in the same column as chlorine. Aluminum is not. Aluminum's in its own category. So the chlorine is with the other halogens, bromine. And yes, chlorine is indeed strong enough to kick out bromine by itself. And so when bromine becomes an element, it's another one that exists as a diatomic element. Just like chlorine here as an element is also diatomic. When I drop and swap charges for my new compound, what I'm going to end up with is Cl2, Al, Br3, goes to Br2 and AlCl3. Now I need to balance it. 3, 2, 3, and 2. Oh, erasing. All right, this last one, again, what I'm looking for is I'm looking to see my element. Who is it higher up in the chart then? Okay. H is in the same chart as it. Chlorine's not even in the same chart. So the question becomes, is Cu strong enough to kick out the hydrogen? Who's on top? Hydrogen's on top, so no reaction. This is why copper is made into pennies. It doesn't react with a lot of things. It's more reactive for sure than silver and gold, which is why it's cheaper. But it still is pretty unreactive for a metal. Okay, let's look at this one. Again, elements don't have to be written first. It's just one capital letter. This element, iodine, I'm looking to see if it's high enough up to kick one of these 2 out. Well, sodium's not in the same column. All the halogens are in the same column. So the question is iodine strong enough to kick out fluorine? And the answer is no.